welcome back to Astronomy Arcade. My name is Victoria, but you can call me Vicky, and I'm here with the discoverer of a planet today. Hi, say hi.
Hello.
He's confused because I'm here with Aiden today. He's thrown off because I'm changing where a bunch of windows are because it's been a couple weeks since I've streamed and I've forgotten where everything goes. Yeah, well,
I'm joking.
I'm able to talk, aren't I?
Right.
But yeah, happy. Today's Thursday, which is weird for an astronomy stream. But Aiden's got things to do tomorrow, and I wanted the exclusive first interview with the lead scientist on the Beta Pictoris D discovery.
The first and only live interview.
Why do you feel so far away? Should I back up too?
But yeah. Anyway, so I've been sitting on this for a minute.
Like since what, February?
I think
January? Okay. Basically right after we moved here, and then I walked into the kitchen one day and he was like, I think we found a planet. I was like, what are you talking about?
Yeah.
And then we've kept our fucking mouths shut since then.
Yes.
So let me get some music going.
Yeah. We had our paper submitted in May, and it was available online since the middle of last month, but
because of weird things with how NASA and ESO allow stuff, we weren't able to talk about it.
Yeah. So, yeah.
But we're here to talk about it now. Chat's popping off. Let me review really quickly. Good morning, everybody. Mom is here. Grant's here. You have symbols by everyone's names now. That's weird. V Mandarine is here. How you doing? Beck is here. Dr. Core Creation's here. They saw you at Exo6, apparently.
Yeah. I don't know who that is. So you don't have to say who you are.
You don't have to say your name. But hello, welcome. Yeah, Aiden was also just at a conference. Well, we were just in Portugal, which if you want to hear about our trip to Portugal, I'll be on stream tomorrow playing Pokemon, and I will talk much about it. I will show you guys the tinned fish, and the music's too loud.
Oh, it's Kadri. Okay. Yeah, it was great to see you too.
Aiden was so confused. He's like, who did I see in person? Who are you? How do you know me?
Yeah.
But, what's it called? But yeah, Aiden was in Portugal, and that was the first time you talked about it publicly, because it was basically the same. No, it was the week after? When did it publish?
The week before.
Okay.
Yeah. Anyway, thanks for tuning in.
Yeah.
So we can talk all about beta pick.
Grandma's here too, and not the brain's here. How you doing?
Yeah.
Everybody's here. Everybody's here to hear about your planet. It's very exciting. Aiden has slides. I considered doing this. I was like, I could do this classic interview style. I used to be a journalist for the school newspaper, but I know how to do interviews, and I was like, I could just have questions for him and everything, but
Yeah, but I've prepared materials.
You've prepared materials?
Yeah.
Why is our color balance so off today? Sorry.
It's cloudy.
It is cloudy.
It's cloudy in San Diego.
Yeah. But.
Yeah. All right.
Where do you want to begin?
I don't know. I mean, there's a few places that we could begin. So, one, I feel like talking about Beta Pictoris like as a star system is useful.
Yeah.
Because it's a star that has a pretty rich history.
It's also important to that will explain why you were looking at it in the first place. Yeah. Because it wasn't really this discovery was a serendipitous one. It was not I think there might be a planet here, so I'm gonna look here one.
Right.
Because you were looking at something else.
This was total luck for me. So,
and listen,
luckiest I've ever been.
I mean, luck, but also like knowing when to knowing how to read the luck, I guess. Yeah. Understanding the data enough to be like, there's something here.
Yeah. It's good to be in a position to capitalize on doing that. Yeah. So yeah, I guess we can start there. And I've taken like a bunch of slides and stuff that. Some of them I presented at Exoplanets. But yeah, I've got a lot of figures.
Cool.
So this is a star, Beta Pictoris is a star that's in the southern hemisphere. So it's not a star you can, I think most of our viewers are in the northern hemisphere. So anyway,
there might be a couple.
Anyway, it's not a star that you can see from like San Diego, or if you can, it like rises like barely. So not something you can observe from the northern hemisphere, which is why it's for a long time it's been being observed by the European Southern Observatory and space-based telescopes. So not being observed from Hawaii.
Yeah.
Yeah. Do we want to share this? I'll take
yes.
a little bit of a.
Oh, it's supposed to be on this screen. There's no difference. There we go.
Do we want to do? Can we present this?
Oh, my music's gone. Can we present it?
Like in prisoner mode.
Mm-hmm.
Just for...
I thought you said in prisoner mode, and I was like.
Prisoner
mode. Let me resize things. I've forgotten how to resize things. Sorry, hold on. It's been a minute. Okay. Why is it so... Hold on. Don't sigh like that. Do you want it... I don't even know how you turn on presenter mode in here.
Well, it's... I don't know. I put it on in... Oh, here we go.
Aha.
All right. Yeah, so...
Oops, sorry. Hold on. I clicked the wrong place.
Yeah, these are slides taken right from... a talk I gave on this at Exoplanets.
Great. You can do the talk. I'm gonna fix things.
This is an image of Beta Pictoris from 1984. So, the sort of claim to fame of Beta Pictoris is that it's the first star that we ever imaged a debris disk around. Yeah, I know, right? This looks. I mean. It's amazing how much our images of the system have improved in the last 40 years. But yeah, this is the first image ever taken of a debris disk. So basically, it's a bunch of dust that is around the star.
Looks like a dirty rug in the garage.
Yeah. So the stars, it would be in the center here, but they've used, I think, basically early form of reference differential imaging (RDI) to subtract the star to reveal the debris disk. So this is high contrast imaging science. So high contrast science is all about getting rid of the star to see what's around it. But basically, what you're seeing here is a bunch of dust that is mostly reflecting and emitting light from the star. And you basically think it is the same thing as sort of the asteroid belt or the Kuiper belt in our solar system, but a lot younger, and so there's a lot more dust there, a lot more material. And that stuff hits each other and creates all this dust that you see. So this was the first time we'd ever seen this image around Beta Pictoris, and it was like kind of the first time that we ever saw something that was like, it wasn't that we saw a planet here, but this kind of indicates all the stuff that you need to form planets is right here. So in a sense, it's like the first direct piece of evidence that there's exoplanets.
Yeah.
Not the first exoplanet that was detected, but sort of a precursor to that.
Mm-hmm.
And it wasn't until 10 years later that 51 Pegasi b was was found. So, and then the other, I'm gonna take you through like a history of Beta Pic. So, the other really notable thing about Beta Pictoris, and this goes hand in hand with the debris disk, is that there's observed what are called exocomets around Beta Pic. So, we have exoplanets, we see planets. There's actually a lot less stars that we see exocomets, which makes sense because comets are really small.
Yeah,
but,
and they're also not... Most of their orbit is not close to a star.
No, right. So. They're usually far out. And the evidence for this is basically that if you look at some of the absorption lines in the star's atmosphere, so this is calcium being absorbed in Beta Pic's atmosphere, but if you watch it over time, you'll see variability in it, and especially it'll be redshifted a little bit from the star's absorption line. And so the idea here is that you have a comet that has calcium as well, that's basically it's falling towards the star, so that's why it's redshifted, and then it's being disintegrated and releasing this gas, and it's causing this absorption feature that you see. So this was not only do we see this disk of dust, but we know that there's at least these large planetesimals in the system. Mm-hmm. And that was also really early in the 80s. So then, there's been a ton of science on Beta Pic over the last 40 years.
It says 2006 behind us, by the way.
Yeah. There's been a ton of science on Beta Pic over the last 40 years. I don't know how many papers, probably over 100. Mostly looking at the disk and stuff.
It's a popular system.
Yeah. But just to sort of fast forward, where Beta Pic science was 20 years ago, is Hubble was observing the star and looking at the disk. So, you can already see it's a little bit of an improvement compared to the first image. So, star's in the center, it's being occulted. You see the primary disk, and then what was really interesting is that you see this sort of secondary disk that's inclined.
I feel like it's a little hard to see just because of all of the color everywhere.
Yeah, it's still noisy.
But it's there.
But it's there. I guess if I showed you one without
the lines and everything, it might help. Yeah.
But, and so at the time, I think there was a few papers that were basically if there's no planets in the system, then a secondary disk like this should just sort of disappear in a couple million years. So the fact that there's a secondary disk like this should mean that it's being stirred up by a planet. Mm-hmm. So there should be a giant planet in there that is at a slight inclination to the primary disk, and it's basically stirring it up and causing this secondary disk. So then, lo and behold, in 2009, they found this planet, such a planet, Beta Pic B. So this wasn't the first directly imaged planet either, so it can't claim that, but it's one of the first directly imaged planets. And I think this was maybe the first time that there was a prediction that there should be a planet there, and then it was found. Mm-hmm. So here it is, and then it was imaged it's been being imaged ever since then. It was actually, even though it was discovered in 2009, they were able to recover it in images from 2003. So we've been able to see it for over 20 years now. And this is just a little gif of it.
Yeah. It seems okay, wait, hold on. It seems to suggest... So we barely saw it when we were blocking out the light from... Is that what's going on?
Yeah.
And then we got better at blocking out light tighter to the star?
Yeah, I got a better chronograph. Yeah. People thought... So this system is very, very close to edge on. Mm-hmm. So there was excitement that maybe the planet would actually transit the star. I think the conclusion now is that doesn't happen. It's probably really close, but it just doesn't happen.
Yeah.
Because it's just this planet's about 10 AU from the star, so it's kind of a little bit past Saturn's orbit. Mm-hmm. So it's pretty far out there, so the chance of the transiting is pretty small.
Yeah.
And this is a huge planet. It's 12 Jupiter masses. 12 times the mass of Jupiter.
Big boy.
It is...
Which is why it was the first one we were able to see from the system.
Yeah. It is sort of near the classical limit for how big you think a planet should be able to be. It's sort of tough to understand how planets can get even bigger than that.
Without just becoming a star.
Well, just even to form like that. Because if they get more massive than that, then you think, well, maybe it really sort of formed more like a binary star.
Yeah.
And it just was low mass, so it was a brown dwarf instead. But the thing is that when you see multiple planets, then you know that this was planet formation,
not a failed binary star.
Not a failed binary. So in 2019, that's what happened, is they found another planet in the system. This is all work that was led by a French scientist, Anne-Marie Lagrange. But they actually found it first in radial velocity, and then they were able to detect it directly with the gravity interferometer, the VLT. So in a sense, it's direct imaging, but it doesn't produce an image that looks the same, so it sort of doesn't produce an image that's very easy to understand, I guess I'll say. This is basically an image on the left. It's an image of the planet, but it's reconstructed from interferometry, so you can't see the star in this image at all. It has like this really weird PSF, and anyway, but the point is it is directly detected. The emission from the planet is directly detected. But this is a planet that's interior to B, so it's actually interior to even Jupiter's orbit. It's around like 2.7 or something AU. I don't remember the exact number.
Is that close to Mars?
Sort of between Mars and Jupiter.
Okay.
But this is also a really big boy.
Big boy.
It's eight Jupiter masses.
Chonky boy.
So it's a big planet sitting pretty close in. So there's an 8 Jupiter mass planet, a 12 Jupiter mass planet. These are both really big planets.
Yeah.
And the reason that they can get so massive is partly due to the star. So the star is like I think the star is like 70 or 80% more massive than the sun. So there's just more mass, and that means there's more metals that can form planets. Bigger stars are better at forming big planets. So then, I mean, JWST has been observing Beta Pic a lot. This is one of maybe the most interesting results from JWST.
Looks crazy.
Which this is with mid-infrared images of it. So we're looking, you can see the scale bar, 100 AU.
Why?
Huge distances, like far beyond Neptune.
Is that a purposeful block out that one sideways plane, or is that a feature of JWST or a bug? I guess.
It's a feature. Well, it's not a feature in that it's not something you want, but it's something that you have in JWST.
Okay.
Yeah.
Got you.
Obviously, if you just rather not have anything blocked out. But the crazy feature, so these are really far distances from the star, but the crazy feature that you see is what they call this cat's tail, which is like, so we have the disk, and then there's some part of the disk that's going out at this just strange angle and being warped.
Yeah, that is weird.
So I think it's still sort of an open question, like, how is this happening?
You didn't solve this.
No, we're not looking at this issue.
Mm-hmm.
But I think the sort of initial explanation is that you might have had a very large a collision of planets somewhere in the outer disk.
Mm-hmm.
I'm not sure what size they'd be. They would be maybe dwarf planets.
Oh, not big.
Sort of Pluto, something like that maybe. Hit each other, out in the outer disk and sent it flying.
Yeah, I mean, Roros just said could be a potential ejection of a planet.
Yeah.
Basically.
So, this is all to say that, like, this is very much... When I think of Beta Pictoris, I sort of think of, like, what was our solar system like in its early, like, very chaotic stages? Because we know that our early solar system was chaotic as well. Our moon formed from a collision of planets. Probably Uranus and Venus also had a major collision of planets.
Because they're fun tilts.
Yeah, they have weird rotation rates and tilts.
Pluto's... does Pluto count too? Because it's got such a wildly...
massive moon?
No, the tilted orbit.
I don't... Yeah, Pluto's orbit's really eccentric. Yeah, I'm not sure if
it's a massive moon. It's basically the same size. Yeah.
And then, like, very early in the history of our solar system, the planets are being bombarded by asteroids. Like, you just get totally smacked by huge objects constantly. Yeah. Like, life's not coming around just yet.
Look at the moon.
So, is a current system stable in the long term? I'm not sure yet.
We've switched back to Beta Pictoris.
Yeah, Beta Pictoris.
Not our solar system.
Probably the giant planets are stable in the long term, but if there's, probably certainly smaller planets still in the system, and I wouldn't know if they're stable. I think the system's still younger than, for example, like when Earth was probably hit by another planet. So, do we have any idea of how old the star itself is compared to the sun? It's about 20 million years old. Okay. A reminder of how old the sun is, please. 4.5 billion. Thank you. Quite young. Very young. Very young. Yeah. One question I have and I'm wondering about is how often the giant planets get hit by a comet or something. Yeah. Because those are just at 12 Jupiter masses, those are just getting sucked right in there. Yeah. 30 years ago, we watched Jupiter get hit by like Shoemaker Levy 9, mm-hmm. and just. Yeah, you have to think that we're seeing exocomets fall towards the star, so you have to think that it's not too infrequent that probably one of these planets gets smacked by a comet. Yeah. Rose says there's estimates that there might be more ejected rogue planets from early chaos in stellar systems than actual planets. That tracks to me. That makes a lot of sense. Because, like, the amount of stuff that you have around a star, and it's like, you look at our solar system that's so stable now, and it's like there's so much empty space, but there used to be just a massive debris disk. It's like, so that stuff had to go somewhere. And some of it went into planets and moons, but not all of it. I do wonder, like, what is the effect of having such a massive planets, especially with the 8 Jupiter mass planet, so close between 2 and 3 AU. Yeah. Like, is it gonna just eat any terrestrial planets that form on the inside? Just consume. Or if not eat them, then throw them into the star or out of the system. I don't know. No. I had to get massive somehow, so. Yeah. No. That's mostly by eating gas rather than, like, other planets. But. It's very, did you ever play that game? It's, like, just a mobile game. It's called, like, agar.io. And you're a sphere, and you just you just consume other spheres. It's very fun. The pond fish game. You just eat other fish. Yeah. Yeah. But you play against other people. And the bigger you are, the slower you go. It's fun. Anyway. So, now getting to the work that we were doing. So I started as a postdoc in San Diego end of last year. Mm-hmm. November. We'll probably learn. So Gaia DR4 is going to be released. I don't remember how long it is until the release. But that'll be really helpful for finding more directly imaged planets. So, because the amount of directly imaged planets is still pretty low. It's, the exact number depends highly on like what you cut off as a planet versus a brown dwarf. But it's on the order of a few dozen.
Mm-hmm.
So. But we observed this system specifically to study Beta Pig B. So we observed it with JWST, with NIRSpec, the near-infrared spectrograph, and our intent was just to get a really good spectrum of Beta Pig B to learn about its atmospheric composition, basically figure out like how metal-rich its atmosphere is, and especially we're trying to figure out the relative abundances of volatile species versus refractory species. So those are species that are usually condensed in solids versus are usually in gas. Mm-hmm. And that can sort of help you figure out how did the planet form? Did it consume a lot of solid matter really early on, or was it mostly accretion of gas? Or anyway.
And you were looking at B because your most of your work normally is in brown dwarfs.
Yeah.
So.
Me.
Well, yeah.
Yeah.
Were you looking at it because it's close to a brown dwarf, and you're looking at the difference between planet versus brown dwarf formation in atmospheres?
Right. So when you look at brown dwarfs, their atmospheres are very. They have the same composition as like stars. They're very similar to the sun. They have a similar amount of metals, whereas we expect planets to be like really enhanced
significantly
metals,
different, yeah,
and maybe to have different ratios of the elements.
Mm-hmm.
So that's exactly what we're trying to like figure out.
Yeah.
So we were observing it for that purpose, and I guess now, are we just sharing the desktop?
Yeah.
Okay.
So you can just open that. It'll be.
Yeah. So.
But don't hover over things. Yeah, because then everything goes away. So.
Yeah. So this is like the base cube that the JWST pipeline produces for the system. So the star is there, and I mean this looks like nothing really.
If they need to see that box, lower it.
So we're observing with what is called an integral field spectrograph, and it basically lets us take a spectrum of the entire field of around the star. So this is like 2 arc seconds by 2 arc seconds or something like that. And we have a spectrum of every single point in it at some spatial resolution. So, for example, this image is, we're looking at the system just at 2.87 microns. And then I can scroll through.
Oh.
And you can see the image at different wavelengths.
Oh,
and
bye. What was that middle one?
So it disappears here because
you can't read or something?
There's actually 2 detectors in the NIRSpec, and they only cover 2 different wavelength ranges.
So there's a tiny little gap.
There's a gap between them.
Gotcha. That's pretty funny.
So you don't have the spectrum at a certain wavelengths, which is dependent on where you are in the image.
Yeah.
But anyway, clearly you can't see any planets or really anything in here.
It's just the star.
It's just the star, and
the
it's
disk.
just.
Yeah.
I mean, you can't even really see the disk.
I feel like you can. I mean, there's a big line that's going through it.
Yeah.
Well, I guess there's 2 big lines that go through it, so you can't really tell which one's the disk. Because it's like.
Right.
Because you see this one, that's like straight across, and then this one that's more. But like, there's other stuff coming off of it, of course. But it just, I don't know.
Yeah, I think that might even just be the diffractions from.
That's
of
crazy.
The star. So when you scale in wavelength, at longer wavelengths, the entire image of the star, the PSF, will like expand, and basically anything that's actually real and physical should not expand, and then anything that's just the starlight will move.
Yeah.
With the exception of this line, that's nothing to do with. That's the clipped region.
Oh, good.
That's just instrumental. So, anyway, this integral field spectrograph doesn't have there's no coronagraph, so we haven't physically blocked the star in any way.
Mm-hmm.
And we basically use like some clever spectral techniques to get rid of the star. So normally, if you do high contrast imaging in like photometric filters, what I'd call like more classical high contrast imaging, you usually use a method like angular differential imaging or reference differential imaging to get rid of the star. Mm-hmm. So reference differential imaging is like, what if we just took a picture of another star that's of similar brightness? It'll have basically the same point spread function, and then we'll subtract it away, and then that'll get rid of like everything.
Yeah.
Angular differential imaging is we could actually physically rotate the telescope, and basically the idea is that the point spread function of the star will stay pretty much fixed, but any planets would then get rotated around, and so it'll let you subtract it away. But we don't use either of these techniques. So I guess first what I'll show you is the first. Oh, I totally forgot about this. So I'll come back to that in a second.
Okay. This is my favorite because I saw this when you were doing the Were you doing a practice for somebody?
Yeah, I was doing practice for them.
And I laughed, and he was very offended. But I was like, "Is that Slack that you have in your professional presentation?" It was very funny. But this is the image that you showed me first.
Yeah, this is like literally a screenshot of when we first saw the planet. So what's happened here is that we've done our PSF subtraction technique. So star's gone. And
star gone.
What this
Dots
is,
left.
it's when I call this an image of the system, I sort of put air quotes around it because it's not really an image of the system like you could look through a telescope and ever see this.
Yeah.
This is a map basically of where in the system the spectrum looks like a planet. So
because you have a code that is looking for a specific spectrum.
We have code that we want to see planets. So this wasn't even necessary for our science objective. We already know where Beta Pic is. So to study Beta Pic, we know B, we know where it is. All we would need to do is just extract the spectrum there. We don't need to create an image of the system.
Yeah.
But we just do it because
it's fun. Why not?
I mean.
And then maybe sometimes you find a planet.
I mean, you want to make sure the planet's where you expect it to be.
Yeah.
You may need to refine where you take the spectrum from. And yeah, maybe there's something you didn't expect. And in this case, there was. So, but yeah, this is literally a cross-correlation map of a planetary spectrum with the spectrum across the entire field. So you get a hit at Beta Pic B because it looks like a planet, and you get a hit here, and that's like, what's that other blob?
What's that other blob?
And for reference, when I saw this was the first time I'd ever done this like technique at all before. So I did not for a second think, oh, that's a planet. I thought, oh, like
noise,
something's messed up, like.
Yeah. Issue with the sensor, or the code is reading something false.
Yeah, like there was a bad image that I need to get rid of or something.
Yeah.
So not for a second did I think this is a planet. I just shared this and was like, I'll just see what JB says, and you know.
JB is Aiden's supervisor, I guess.
Yeah, he's a research scientist at San Diego. So, and so then like. He says, can you plot the spectrum from that location? Which is the clear next thing to do if you want to figure out if it's real at all. So let me do this, and this is like the very crappy like image you just
If there was another planet, they would have found it already. Duh. Aiden, probably.
Well, yeah, and that's...
Actually, though,
but that's...
he's like, so many people have looked at... I mean, you said in the beginning, there's been hundreds of papers on this system.
This system has been imaged, like, every year, or at least every other year, for the last...
20, 30 years.
20, 30 years.
Yeah.
So, certainly I did not think... That was not even a possibility in my mind.
No.
But here's the spectrum. I haven't labeled it at all because I literally, I just made this to send to JB. So I didn't label the axes. It's not a good plot. But
don't judge him on this graph.
It's from 4.2 to 5.2 microns. And I feel like if you don't look at planetary spectra, this looks like nothing. Like, it looks like garbage.
Correct. It looks like there was an earthquake somewhere, and you're looking at a seismometer.
Yeah, but this is actually a very clear signature of carbon monoxide, and even though, so this here is like noise.
Becca goes, that sure is a graph.
This is pretty much noise.
Yeah, but
this is not noise. This is a very regularly spaced absorption lines, and from basically 4.5 to sort of 4.9 microns. That is exactly the absorption spectrum of carbon monoxide. Which carbon monoxide only exists in very cold stars, brown dwarfs, and giant planets. So just from this, it's like, this is probably a planet.
Yeah. Because it can't be another star. You would have seen it.
No, it can't.
And it can't be a brown dwarf with another
right. So
planet orbiting.
The only, basically, just from this, the only possibility that it's not a planet is a sort of like pathological thing where you have a brown dwarf or star that's relatively close to Beta Pic, because it has to be in order to be at that brightness. Because if brown dwarfs are much farther away than Beta Pic, then they're just not going to be visible at all. And the other thing is, this is, if I go back here, so you can't see the disk, but if you draw a line between B and where the star should be, which is here, that falls right in line with that. So it's right in the disk plane.
Yeah.
So the chance that there's just a brown dwarf, not in the system, but just sitting in the disk plane, the chances are like nothing.
Yeah.
So now, when I saw this, I still didn't think, oh, it's a planet. The reason being is because I was like, well, perhaps one of the images was like misaligned or rotated or something, and it's actually just a ghost of B that is somehow got in the wrong place.
Yeah. Like,
we just didn't align it right or something, and yeah. Now, does that actually make any sense? No, it doesn't. but you always think, you have to think, what are the problems that might cause this before you actually get excited.
Yeah. Well, yeah, the whole day, because this was all kind of in the same day, right?
Yeah.
Yeah, and so he's sitting at the kitchen table because he was working from home, thus Slack. And I keep coming in to, like, get my coffee or, like, get some water. And the day started with, look at, there might be a planet. Probably not. To, like, I think we found a planet. The gradual progression.
Yeah.
And for a while you were like, no, it's not. It's not. You would flip-flop for like the week.
Yeah. I don't know. I just...
Well, I mean, it's tropical.
Out of my expectation. I'm going to come back here. So, I was unaware of this, but it turns out that there had been predictions that there needs to be a planet. Another giant planet in Beta Pic. Or at least gaseous planet. So this was a paper from last year that said, in order to explain... So we've measured basically the inner radius of the debris disk. Mm-hmm. And it's around 40 to 50 AU.
How?
How have we measured it?
I'm sorry, did you... Because you originally said that the
Yeah.
it's pretty like flat on, right?
Yeah.
So how do we get this?
You sort of measure. You can measure the sort of the density profile as you go out, and you can see the density drop off. Especially, there is actually some gas still in this disk, and that's easier to see that the gas just like cuts off.
Oh, okay, gotcha.
So yeah, there was a prediction that actually there needs to be a planet orbiting, somewhere around 30 AU.
Because it's so much lighter there? Is that like, because there's less?
Basically, like, B, despite the fact that B is so massive, it just can't carve the disk like this.
Yeah, it couldn't have, like, cleaned up the disk in that way.
Exactly.
Yeah.
So there needs to be another planet that's, like, cleaning up the disk.
Yeah.
But even though there were these predictions, they predicted that the planet could be really low mass. Still giant, but it could be like a Neptune or something.
So like
that's not detectable.
Able to see, yeah.
So there was no people weren't like, based on this prediction, people weren't like, oh, now we gotta observe Beta Pic again. It was
because it was like you could try to observe it for a long time and still never see it, because if it's super small, then it's like you're just wasting your time.
Yeah, exactly.
So, also, question: how far? You might have said this already. How far away is this system?
About 20 parsecs. So like 70 light years.
70? Okay. 60 or 70 light years. Okay.
Yeah.
Thank you. It's far.
Yeah. Yeah.
Beta Pictoris isn't even my final form yet.
So this is like when we actually. This is like the map that you make really quick because it's just easy to make.
And you have to send your boss something so he knows that you're working on something.
Exactly.
Yeah. No, I get it.
And this is like the map you can make when you run a forward model that takes like a day to run.
It says Gibbs et al.
So basically we run this forward model that both like fits the star and a planet at the same time, and it sort of fits that everywhere in the field, and if there's no planet there, then you get nothing. If there is a planet there, then you get a hit. And so that's why I mark out the disk plane here. You can't see the disk at all because it doesn't have a spectrum that matches a planet.
Show up, yeah.
So it's gone. But yeah, this makes it very clear. B and D. And then, so this was our original program that was meant to just study B. So from 4 to 5 microns, we got it really, really well. And then we also get 3 to 4 microns. And originally, we actually did not see the planet at all there. And part of that was a mistake on my part. Part of it was just bad luck. So on one hand, we would expect that the planet should be a lot less visible in these wavelengths. And that's because from 3 to 4 microns, that's where methane absorbs. And usually that sort of tanks the spectrum, the flux from planets. So the planet will be relatively bright from 4 to 5 microns, but from 3 to 4, flux drops off a lot. Gotcha. Like order of magnitude, maybe more. So. And
Rover's had a question. This is just a general for this whole section.
Where's C?
Where is C in this? Because there was a second discovered planet before yours in this system.
Yeah.
So why weren't when you saw the data, why were you not like, oh, that's the second planet?
Yeah. So C is interior to B, and we know where C is, and it's way too close to the star to be seen.
Oh, okay.
It's in this clipped region, so you just can't see it at all.
Because C was not directly imaged. You said it was transit.
Radio velocity originally, and then they've used an interferometer that has much better angular resolution, I guess you'd say, to image it. But yeah, J2ST is not capable of seeing C.
Gotcha. Okay.
And there's really very few instruments that are. It's really just gravity.
Yeah.
So
C is in these photos, technically.
Yeah.
It's just not labeled because it is also the star, basically.
I also think that C just happens to be also almost behind or in front of the star at this point. So.
Also, by the way, for anybody who's less used to astronomy and naming conventions, the reason they don't start at A is because that's just the star.
That's right.
Beta Pictoris A is the star.
And then, so we did a director's discretionary program with J2ST, which is basically where you apply out of cycle. You say, oh, we have this result that we think is really interesting, but we need more data and we want to get it quickly. Can
we do some emergency observing?
Yeah.
With your big
Usually
telescope.
People do these for time domain things like, oh, there was a supernova or something like that.
We only have this many, months to see it.
Yeah. In this case, we didn't see D at all in 3 to 4 microns, and we thought this might be a subjovian planet. So, which would be...
What does that mean? Yeah.
I mean, there's I think maybe only one or two subjovian planets less massive than Jupiter that have been imaged.
Yeah.
So that would be very significant to detect a subjovian planet. We were thinking maybe this is the fit.
Imaged,
right, directly imaged.
We found other ones that are smaller, but not with this method.
At the time, we were thinking maybe this is potentially the faintest planet ever imaged.
Yeah.
Did not turn out that way. It's not. So.
It's so exciting.
But yeah, it doesn't mean it's not interesting.
Charlie said that, the supermassive black hole at the center of the Milky Way is a perfect example. Sagittarius, A star. Because the stars are always A. What about in a binary system? Is it A and B?
Yeah.
Okay.
But they capitalize.
Oh, so that's why these are all lowercase.
Yeah.
There's a difference.
Exactly.
I see. C is 2.7 AU away, so it makes sense to why it's so much harder to see. Yeah, exactly.
Yeah. And then we also we have a guy in our collaboration who's really good with J2ST's mid-infrared instrument.
Miri.
So did mid-infrared spectroscopy. Now in this case, we actually don't image the star at all. We just put it off of the star. Now that doesn't, just because you put the star off the detector doesn't mean that
the star won't affect the image.
Exactly.
Kind of thing. Yeah, the starlight.
It doesn't get rid of the PSF still leaks into where the detector is.
Yeah.
But
just because you take a picture where the light bulb is not in the photo doesn't mean the light bulb won't have an effect.
Exactly.
You can't turn it off.
Yeah, if it worked like that, then direct imaging would be way easier.
Can we just switch off Beta Pic for just a second, just so we can take a picture really quick, and then we can turn it back on.
But anyways, you at least get rid of the saturated region, because the star just completely saturates the detector. So this is the technique used for Miri, and that's why there's no other half of this image.
We need more zoom and enhance. Yeah, imagine if you guys had the magical technology of all of those shitty crime movies and TV shows where they enhance in the 90s, and you see a very clear image of someone's face from 50 yards away, and you're like, yeah, that's real. Okay. For sure. Anyway. So,
I guess I'll say a little more on the 3 to 4 microns. So, it turned out that the reason that we didn't detect it originally here was that, so we do actually roll the telescope. We do 2 observations for each of these images. And basically between the observations, we just roll the telescope slightly so that everything just moves a little bit. Mm-hmm. The reason for that is that
to make sure nothing.
Sometimes you can just have a bad region in the detector.
It's like a camera sensor. Pixels burn out eventually, and JWST is new enough, but there can always be issues with the spots on your.
So, it turned out that one of our rolls for the first image was bad, and we didn't detect it at all in that. But in the second roll, it was actually findable. So it was sort of my mistake in that I only looked at one roll first and was like, I don't see anything. and I didn't look at the other rule.
Yeah.
Now, I will give myself a little bit more lenience for not doing that, because actually it's still really not visible in the other one.
Yeah.
Because we don't have as many images to stack. But in the spectrum, you can tell that it's there. But anyway, it's much more marginal. But, I guess... So, this is like highly technical, but to say sort of how we do this, so we don't have a chronograph and we don't use the sort of classical high contrast techniques. The way that we do this is that we say, so the game is getting rid of the stellar PSF, and a game that we can play is to say that, let's just sort of accept that we can't do as good a job as we want to in like exactly subtracting the stellar PSF.
Yeah.
So let's make a sacrifice. We'll make a sacrifice to be able to sort of get around that. And the sacrifice that we make is basically removing what's called the continuum from the entire detector. So when you think of a spectrum of any object, there's what's called the continuum, which is sort of the smooth part of the spectrum. It's like how it varies over large wavelengths. So in this case, the continuum is this sort of purple line.
Yeah.
Like low frequency, how it changes over a broad wavelength range. It's sort of often related to just the black body radiation from the object. As opposed to, you have the high frequency sort of non-continuum component that's actually like emission and absorption lines. So that's all these small features that you see.
Yeah.
So what we do is we basically, first we get a really good spectrum of the star. So there's starlight all over the detector. And we basically use that starlight that's all over the detector to get a really good high frequency spectrum of the star. So we can't get the low frequency continuum spectrum of the star because that depends all on how strong the speckles are, which requires modeling the PSF really well. But we can combine all the light from all over to get a really good high frequency spectrum of the star. And then we say that we'll just reconstruct the low frequency component flexibly. Like, we don't actually know what it is, but we'll just make it up and we'll multiply our high frequency spectrum by a spline that will just adaptively fit it. So essentially we're just going to remove the continuum from the entire detector. What that means is that if there's any continuum flux from a planet or from the disk, it's also just going to get subtracted. So what that means is that we end up just seeing the high frequency spectrum, like no continuum of everywhere on the detector. So that's why when I show these spectrum, so there's a flux and they're at zero and they go negative and positive. And that's because, so clearly the star can't have a negative brightness, but the idea is that we've subtracted away that continuum. So this means that we actually literally do not know how bright the planet is. We can set a limit on it, but we cannot directly measure how bright the planet is. It lets us image planets that are really faint, but we don't, like, it's impossible to measure exactly how faint.
Yeah.
That's the drawback of this. But we know that the star is at least as bright as however deep, or the planet is at least as bright as however deep the lines are, but beyond that we don't know. So anyway, I realize we're running out of time, but I mean we can go longer.
Yeah.
If we want to.
We can go longer.
Yeah, so we saw CO, we saw methane, and we saw water at these different wavelengths. This technique that we use is only possible when you have a high enough resolution in spectroscopy. So you can't do the same thing with images, like photometric images across the board. Yeah, doesn't work. You have to be able to separate like the high frequency from the low frequency spectrum. Yeah. Anyway, so this is how the spectrum like fits to a model. Anyway.
We'll see you next time, Charlie. Thanks for popping in. And he said congratulations before and everything.
Appreciate it.
So. We'll see you next time.
So. I'll talk less about this, but whenever you discover a planet, the sort of basic things that you want to know before you start studying its composition and how it formed, you just want to know how big is it, what is its temperature, and what is its orbit. So that's what we tried to do. So this is a plot. So we have evolution models for basically how planets and brown dwarfs cool over time. So they form, they're really hot because gravity contracted a bunch of mass and it heats up when it contracts. Mm-hmm. And then over time it's just going to cool off. And so at 23 million years old, we know how hot planets of different masses should be. So that's what this black line is for the system age. How hot should a planet of this mass be? So we can put Beta Pic B on there, and it lines up pretty well. It's 12 Jupiter masses, and it's about 1600 Kelvin. Beta Pic C, I guess I said 8, it's maybe more like 9 Jupiter masses, and it's a little hotter than 1200 Kelvin. So then we need to figure out what the temperature is, and we can't directly measure the mass, so we just have to figure out what the temperature is, and then figure out what
sort of on the line.
Yeah,
and see
figure out what mass. So this was pretty tricky for us because when you get rid of the continuum, you get rid of a lot of information about the temperature. Mm-hmm. So what we end up doing is that we basically need to use the chemistry that we see and backtrack to that temperature, which doesn't work that well.
And Roro was just wondering, does this account for distance too, or only mass?
This accounts for the distance as well. Yeah.
Derailed.
The if you mean distance from the star, these planets are all too far from the star for their temperature to really be altered by the star. Mm. So in the end, I'll just say that we sort of concluded it's in the 600 to 800 Kelvin range. So probably about 2 to 4 Jupiter masses. It might be even a little bit less than 2 Jupiter masses.
Yeah.
It's almost definitely more massive than Jupiter, but not by much.
Yeah.
So, it's like a young Jupiter.
Rose, it's not your fault. I said I derailed him. I picked when I read the questions. Also, V Mandarina, we did talk about it a little bit in the beginning, but we can go over it again. So Aiden was looking at the Beta Pic system, specifically at Beta Pic B, the other large planet that's been in some of these photos, to look at the atmospheric composition.
Yeah.
And then there was a blob. That was not the planet he was looking at, or the other planet that they knew about. So we were like, what was that? Well, you were like, what was that? So it was an incidental sort of thing, which is pretty cool.
So, the other thing we want to do is fit an orbit to... That's sort of like one of the things that you have to do to confirm the planet is...
It has to...
You have to figure out that it
where it moves.
Right, and it has to make sense. Like, if you see the orbit is going off at 90 degrees, that's not possible. So that would not be a planet. Yeah. So we image where it is. We actually, even though we have two different observations, we can't like resolve. We can't resolve any movement of the planet. This is going to be on of a 90 to 100-year orbit, so it's not moving very much. And we basically observed 4 months apart, and we couldn't see it move. But the thing that spectroscopy gives us, and this is another sort of unusual and really powerful thing, is that we could directly measure the radial velocity of the planet. And when you do that, it basically matches exactly with where it is relative to the star. Mm-hmm. So just from the image and the spectrum at one time, you can fit an orbit that's fairly reasonable. There's still a lot of like possibilities. Is it 35 AU? Is it 25 AU? It's all still possible, but nevertheless, we can say it's not like it's not super eccentric. It's not going to go out to like 100 AU or something like that. So. Mm-hmm. And then we had a scientist at Caltech do stability fitting for us as well. So basically, we want to check. Okay, this planet's here. Is it stable with the inner planets? Because if it's not, then that means it's like it sort of will throw doubt on if it's a planet because
if everything else is stable and this one's not, then
right,
it's probably not.
And if it's unstable, then why isn't it already collided or gotten thrown out or something? So yeah, based on based on how the blue shift or red shift compares to the baseline. And anyway, so from the stability analysis, that was kind of suggesting that the orbit needs to be farther out. I guess we're sitting about here. So the lighter color here is more stable, a higher fraction of stable orbits. So it increases as you go out, but our orbital fits kind of are better on the inside. So right now I'd say, I think it's orbiting sort of around 30 AU, which is pretty close to where the prediction was for this planet.
Yeah.
So it was a good prediction. Yeah. So the other, very interesting and dramatic part of this is that we weren't the only people to see it. And it's actually crazy because our original observations were on Thanksgiving, and their observations were like 5 days later on December the 3rd. But they didn't use the James Webb Space Telescope. They used a relatively new instrument at the Very Large Telescope in Chile. And they used more sort of classical high contrast techniques. I do think this gives you maybe a better perspective on how the relative brightness of these planets. So their method, their method isn't quite as good at getting rid of the disk, so you can still see it there, although it's pretty faint. But you can see just how incredibly bright B is compared to D.
Yeah.
Which is much fainter. Yeah, and then I think the really interesting thing that they did is they did the work of going back and looking at past observations
to see if they could
find it, which was necessary in their case because, so typically to confirm a directly imaged planet, you need to confirm proper motion. Already the fact that it's in the disk, that's pretty good, but for it to be definitive, they need to confirm that the planet moves with the star and doesn't get left behind or something, because you could just again have a star that's randomly sitting here. Mm-hmm. But they did that and they tracked it back. So they tracked it back in JWST NIRCam observations from a couple of years ago, and then they actually were able to track it all the way back to 2014. That's crazy. And you think, why didn't they
notice it?
Why didn't you notice this? But the data analysis techniques that we've been using to look at these images has improved. It's constantly improving. So
they're looking at data these are images that they have, or data reduction that they have done this year.
Yes.
But so these are not the images that they would have seen in 2014, 2019, 2020.
No, exactly. These are not the images that people saw in these years. These are re-reductions with new, more advanced methods, and lo and behold, it's there.
So people weren't looking at these and being like, I guess that's a little bright spot. Well, we'll ignore it.
Yeah. often if you see something that's really low significance like this, it's like this happens a lot and it's just nothing.
Yeah.
Like it happens a lot and it's nothing. I mean, this right
in
here.
theory, it could be just
This is nothing.
Yeah.
And it's not really that much fainter.
Yeah.
So, yeah. And the other crazy thing that they found is that, so I think the headline on their sort of press release, and it's been picked up by a lot of the press articles about it, is like a game of hide and seek. Because what they found is that back in 2014, that D was actually almost in the same place as B. So the two planets were almost like visually on top of each other.
So then it was like, yeah, you'd obviously only see B.
Right.
Because that was what you were looking for, and
yeah.
It's way bigger.
So in all in these 5 images, this is the star that's being subtracted. In this image, that's B that they've subtracted.
That's interesting.
Yeah. So that's crazy. So that's part of it too.
Yeah.
Yeah.
D must be really far out because it really doesn't move, huh?
No. It
seems to really
it's
stay
going pretty slow.
Yeah.
But I think maybe sort of 20 years ago when B was first discovered, D would have been like almost on the star.
Yeah.
So.
Yeah, 2 different methods, 2 different instruments in a sky full of countless systems to focus on.
Yeah.
The coincidence is uncanny.
Yeah. It's crazy. Yeah, D is like Neptune distance. The other thing that's really interesting here is that in this system we see 2 massive planets on the inside and then one that's less massive on the outside. And we see the same thing in our solar system, where we have 2 massive planets, Jupiter, Saturn, and then 2 more less massive planets on the outside.
Yeah. And in theory, since the biggest one that the closest one that we know of is at like further than Mars distance, there could totally be terrestrial planets closer that we just couldn't see.
Yeah.
So it could mirror our system quite well.
Yeah.
Just larger in general.
Yeah.
And Becca, the line that's going in between the 2 planets, so that's the debris disk that's around the star. So that's just more like gas and dust that the planet's formed from, and it's just hanging out.
Yeah. We're able to subtract it better in our images because
you're not looking. You're looking for signatures of certain elements. Not
exactly. We use the spectrum.
Brightness. Yeah.
We use the spectrum, whereas they don't have the ability to use the spectrum to do that. So this is the plot that exists in every direct imaging paper except not ours. That basically shows that it's a planet because it shows basically if it's a planet, it needs to follow this line, and if it's not, it'll do this. So that's based on parallax.
That's very funny.
It makes these little circles due to annual parallax.
Huh.
And then they also fit an orbit that is honestly really similar to ours, which I'm actually very proud of this because we were able, from basically one data point, we were able to get an orbit that is quite similar to the orbit that they get from tracking it for
data points.
Over a decade.
Yeah.
So I think that's a big win for us.
Yeah.
And then they compare its like different photometric colors to other planets and stuff. So.
Airy.
And then NASA did a press release for us because this is very, it's a storied system. So they had their graphic designers.
So it's the closest one to us in this image?
Yes, this is D.
Wow, there she is.
And then that'd be B and C. Obviously, it's a concept, like, not to scale. In a real image, if you were able to see D that close, then both of these would just be points of light. But nevertheless, it's, gives you the feeling.
We like an artist concept in this house.
Exactly. It gives you the feeling.
Yeah.
And then they made these...
I told Aiden when he got this, because we were on vacation, he was like, oh my god, they made an artist concept of it, and they're like they asked for your approval or something?
Yeah.
And I was like, You got fan art of your stuff before I did? How rude.
It's not fan art.
It is fan art.
And then they made this really nice, like, cleaned up version of our detections that you showed.
Yeah.
That I showed.
It looks nice.
Showing, here's D and here's the carbon monoxide spectrum. This is kind of weird because I don't know. It's just knowing what they started with. It's kind of weird, but you can see like the size of Neptune's orbit and B and D. So.
But where did they put the Slack messages?
Yeah, and that's kind of the story. So
that's the story.
I think there's going to be a lot of work, more papers on the system, because it's interesting how this planet interacts with the disk, because it's probably carving the inside of the disk.
And it doesn't seem like it's done either. There's a lot of other stuff that's like in there.
Yeah.
So,
it probably stirs up.
System.
It probably stirs up a lot of the exocomets that are falling towards the star. We still really only know the basic properties of the planet, so we're going to want to learn more about its atmosphere. Mm-hmm. Yeah, and it's this is now only the second system for which there are more than 2 directly imaged planets. So there's one other system that has 4 directly imaged planets. This one has 3, and there's no others that have.
What's the other one?
HR 8799.
It doesn't even have a name?
No, I don't. I mean,
this is Beta Pictoris, like the HR. Jesus.
It's a dimmer star.
But they can still see them.
Yeah, this is a really bright star. That's why it's Beta Pictoris.
Mm-hmm.
Second brightest star in picture. But yeah, that's how an exoplanet gets imaged.
Yeah.
I will say, if to just toot my horn, this is the first time that spectra of this resolution have been used to basically discover the planet. So never before has a planet been imaged and we've seen like carbon monoxide, water, and methane from the observation that discovered it.
Yeah.
And it's also like the very first time that we've basically confirmed a planet from what really could have just been one observation.
Yeah.
Like usually you see these planets and then you got to come back to a year or 2 years later and make sure that it's...
I mean, that's what they had to do with the...
Exactly.
Even though they were looking at old data, that's what they had to do for the other team that observed this.
Yeah, and we really didn't have to do that. We kind of did a little bit. We did a follow-up observation because to be honest, we were kind of like, are people going to believe us? Like, they're going to say that it's just some instrument thing, so
even
we
if
need to see it again.
Even if you're confident with the first data point, it's sometimes just better to have a second. Yeah,
and I guess the last thing I'll say is that this is a method that's really good at getting rid of disks, which if you're a disk scientist is not good, but it's really good at getting rid of disks, and all stars have disks, and if you want to image really faint planets, you need to get rid of the disk. So we're kind of hoping that this resolution of spectroscopy will be picked up for like will be used on like the next generation of telescopes to help like increase high contrast sensitivity. So yeah.
Rose said so happy for you. Thanks, Rose. Congratulations to you and your team.
Yeah.
You'll probably get around to reading the paper sometime. You can read the paper. You can read some of the articles that they're Aiden's paper has been picked up by several of the news organizations covering it. Unfortunately, your SEO is not the best for the publication title. They did not put the name of the planet in the title, so some people... And also because of NASA and ESO's weird rules about... Because the other team only had to deal with NASA's rules, right? Or no, they dealt with ESO rules, and
Yeah.
you guys had to deal with NASA and ESO rules, and they're very confusing as far as when you can publish and talk about things versus when you can have a press release, and there's like a weird thing, so Aiden's team had to wait longer for sending things to reporters, so that's a whole thing. You read the article on NASA. That's cool.
Yeah.
Are you in that one?
Yeah.
Nice.
Yes, yeah.
It's cool that there was another team that found it another way because it reinforces that you got it right. Yeah, that's the one thing. Because I was like, can I talk about it a little bit?
Sure.
He was like a little upset when we found out that there was another team because it was sort of towards the end of the thing, and they found out there was a second team.
And I'm sure the other team was upset.
Was upset too, yeah, because it was just like, but then they talked and agreed to publish the same day and stuff, but like it's still it's a little bit like you find out that your competitor is also releasing a movie about bugs. It's 3 months away from when you're releasing your movie about bugs. I'm talking about you, Bugs Life, and what's the ant one? From DreamWorks. Ants. Yeah. It's just called Ants and A Bug's Life. They released like within 6 months of each other. They were definitely both working on those ideas independently.
Yeah.
And
But I think it's.
But also, yeah, the good part was you immediately have someone verifying your results.
Yeah. The great thing about it is that we used 2 really different methods and got pretty similar results. And I also think that it kind of helps show the power of our method. It sort of hasn't gotten the SEO, as you say, that we maybe would like. But
I don't know why you didn't put the name of the thing in the title.
But it kind of shows like here's how it was discovered in a classical way, but look at how we did it in a totally new way. So
yeah, which is exciting because like granted, like the other team used technology that is newer and therefore better, so it was more sensitive. But you guys used a fully new method, basically.
Yeah. Which
is really exciting because you can apply that new method to a lot of stuff.
Yeah, and I would actually say, there's right now our methods are exclusive because there's not an instrument that can do both.
Because it has to be on JWST.
Yeah, our method has to be on a space telescope, basically. But they're not actually mutually exclusive. You can do both of them, you just have to design an instrument that can do both of them. So,
yeah. And now the real questions. And comments. I would love to be a fly on the wall at Aiden's performance review at work. Discovered a planet this year. What are your goals for the year ahead? You were like, I've peaked. Becca's real question. Does discovering a planet get you a raise?
No.
Damn.
Yeah.
But your boss, advisor, Quinn's very happy.
Yeah, I think we're all. It was the most interesting thing I've done.
Yeah.
Ever. So.
It's exciting.
Yeah. All right. Well, thanks everyone for joining.
As far as the rest of the week goes, I'll be here tomorrow. So we just switched gaming and astronomy this week. So I'll be here tomorrow playing Pokemon Violet. And if you want to hear about our trip to Portugal, Aiden was at a conference for a little bit of it, but then I showed up and we had a bunch of fun. So I will also be talking about that plenty tomorrow while I fight some Pokemon. So come hang out at normal time, 9 a.m. Pacific. And then next week we'll be back for a normal week, Tuesday, Thursday, Friday, the usual. If you're new here, we had a couple new people. If you're new here, you can follow us and come by. We talk about astronomy at least once every other week, usually. So the depending on Aiden's schedule, but we usually do Friday mornings. And you can come by. We could talk about fun stuff. And I also play D&D in space with my friends on Tuesday, and I play a video game on Thursday mornings as well. Everybody's saying thanks and congrats. Congratulations. Grandma said congrats. Mama said congrats. Please don't accept an invitation to the White House. They don't believe in science. I don't think he's going to get one, but if he did, we would spit on it and throw it away. Don't worry. But, yeah. Then, follow if you're new here, subscribe if you feel so inclined. You can, let me do the things. Oh, Grant's got it. You can join our Discord. If you're not on there, we talk about stuff there. That's where Aiden posted a couple links to the actual articles. It's in the astronomy chat in there. So if you guys want to check out some of the articles about his paper, they're in there. Did you link your actual paper?
I don't think I did.
You should.
And
you
if
can
people
pin
want
it.
to chat about it more.
Yeah, Aiden will answer questions and stuff.
I'm not always the best at the Discord, but
I'll tell him. And then you can check out our VODs on YouTube. This one will be going up. I'm probably gonna put it up like tomorrow. I have to check my window because I always do a week, but I think Twitch allows me to put it up on YouTube after a day. So this will be up there. And then follow us on Blue Sky. Follow us on Instagram. And it's hyperlinked to the NASA article. Rose got it. Thanks, Rose.
all right.
And I think that's about it.
Yeah. Have a good day, everyone.
We'll see you guys next time. Bye.